Water covers 70% of our planet, yet only a fraction is drinkable. As droughts intensify and demand grows, the global water crisis is reaching a breaking point. The solution, desalination, is energy-hungry and unsustainable. But what if we could make it clean and efficient? Welcome to Eco-Innovatech. Today we explore how nanotechnology is transforming desalination, using atomic-scale innovation to bring affordable, sustainable fresh water to billions. Reverse osmosis, or RO, dominates global desalination, but it consumes massive amounts of energy, up to 15 kilowatt-hours per 1,000 gallons, and membranes often clog with salt and bacteria. Engineers realize the real problem lies within the membrane itself. Reverse osmosis, or RO, dominates global desalination, but it consumes massive amounts of energy, up to 15 kilowatt-hours per 1,000 gallons, and membranes often clog with salt and bacteria. Engineers realize the real problem lies within the membrane itself. The reverse osmosis process, for all its ingenuity, has long been constrained by the very heart of its system, the membrane. For decades, the industry standard has been the thin-film composite polyamide membrane. A remarkable material, certainly, but one with inherent limitations. Its structure is a random tangled mesh of polymers, often described as a bowl of spaghetti. This disordered arrangement creates a tortuous, uneven path for water molecules. To force water through this microscopic maze requires immense hydraulic pressure, which is the primary driver of the high energy consumption we've discussed. Furthermore, this same irregular surface is prone to fouling. The accumulation of salts, organic matter, and microorganisms that clogs the membrane reduces its efficiency and shortens its lifespan. For years, the desalination industry has been in a constant battle, optimizing pressures and pre-treatment to fight against the fundamental physics of these membranes. But what if the membrane itself could be redesigned from the ground up, atom by atom? What if, instead of a chaotic maze, we could create a perfectly ordered superhighway for water? This is where the story of desalination takes a turn into the realm of nanotechnology. Enter graphene and carbon nanotubes, revolutionary materials built from the most fundamental of elements, carbon. Graphene is a material that, until recently, existed only in theory. It is a single, flat sheet of carbon atoms arranged in a perfect hexagonal honeycomb lattice. It is the thinnest material ever created, literally 1 atom thick, yet it is over 200 times stronger than steel. A carbon nanotube, or CNT, is essentially a sheet of graphene rolled up into a seamless microscopic cylinder. These are not just incremental improvements. They are a paradigm shift in material science. Their unique atomic structures offer properties that seem almost purpose-built to solve the core challenges of reverse osmosis. They promise a future where membranes are no longer the bottleneck, but the enabler of hyper-efficient, low-energy desalination. Let's first examine graphene. The magic of a graphene membrane lies in our ability to engineer it with atomic precision. Using advanced techniques, scientists can perforate the graphene sheet with billions of nanopores, tiny, uniform holes. The size of these pores can be controlled with incredible accuracy, tuned to be just large enough to allow a water molecule to pass through, but small enough to physically block larger salt ions like sodium and chloride. This is the principle of size exclusion, taken to its ultimate limit. Unlike the random pore distribution in polyamide membranes, these graphene nanopores are perfectly straight, uniform channels. There is no tortuous path. Water molecules can pass through almost as if through empty space, dramatically reducing the hydraulic resistance. Think of it as the difference between forcing sand through a dense, tangled sponge versus pouring it through a perfectly constructed sieve. The sponge requires pressure. The sieve works with gravity alone. This near-frictionless transport is what allows for such a profound reduction in the required pumping pressure. Carbon nanotubes offer a similar yet distinct advantage. Their interior channels are also incredibly narrow and, crucially, atomically smooth. This smoothness is key. At this nanoscale, the interactions between the water molecules and the walls of the channel become dominant. The carbon atoms in the nanotube's wall create an exceptionally low friction, or slippery, surface. Research from institutions like Lawrence Livermore National Laboratory has shown that water can flow through these nanotubes at rates thousands of times faster than classical fluid dynamics would predict. The water molecules form an ordered, single-file chain, zipping through the tube with minimal resistance. This phenomenon, known as fast water transport, means that a membrane made from an array of vertically aligned carbon nanotubes could achieve incredibly high water flux, the volume of water passing through a given area of membrane per unit of time, at pressures far lower than conventional RO. Beyond their extraordinary permeability, these nanomaterials also present a powerful solution to the persistent problem of fouling. The atomically smooth surface of both graphene and carbon nanotubes offers very few sites for bacteria, minerals, or other foulants to attach to. It's like comparing a rough, unpolished rock to a perfectly smooth pane of glass. Algae will readily grow on the rock, but struggle to gain a foothold on the glass. This inherent anti-fouling property means nanomembranes could operate for much longer periods between cleanings, reducing operational costs, chemical use, and downtime. Furthermore, scientists are exploring ways to enhance this effect. By chemically modifying the surface or applying a small electrical charge, a concept known as surface charge manipulation, these membranes can actively repel charged particles and organic molecules. This not only prevents fouling, but can also boost salt rejection, creating a dual-action membrane that is both highly permeable and incredibly robust. So, what does this all mean in practical terms? The numbers are staggering. Pilot studies and theoretical models from research groups at MIT, the University of Manchester, and others project that graphene and CNT-based membranes could slash the energy use of desalination by a significant margin. While claims vary depending on the specific design and salinity of the water, conservative estimates suggest energy reductions of 30 to 50% are achievable, with some optimistic models pointing towards 80% or more under ideal conditions. This would bring the energy cost of seawater desalination down from the typical 3 to 4 kilowatt-hours per cubic meter to potentially below 1.5. This isn't just an incremental gain, it's a leap that could redefine the economic viability of desalination globally. The high permeability also means you can get more water from a smaller membrane area. This leads to a smaller physical footprint for the entire plant. Instead of massive industrial complexes, we can envision smaller, more modular, and decentralized systems. Of course, translating these incredible nanoscale properties into a large, durable, and cost-effective membrane is a monumental engineering challenge. This is the frontier where lab-scale discovery meets industrial-scale reality. Early prototypes faced issues with defects. A single tear or an imperfectly formed pore in a graphene sheet could compromise the entire membrane's salt rejection. Creating a perfectly uniform, square-meter-sized sheet of flawless graphene is still beyond our current capabilities. Similarly, aligning trillions of carbon nanotubes perfectly upright and packing them densely into a stable membrane has proven difficult. However, researchers are making rapid progress. One promising approach involves using graphene oxide, a form of graphene that is easier and cheaper to produce in bulk. These sheets can be stacked, and the spacing between them acts as the filtration channel. While not as perfect as a perforated single sheet, these stacked membranes are far more ordered than polyamide and have already demonstrated significant performance gains in lab settings. Companies are now developing roll-to-roll manufacturing techniques, similar to printing a newspaper, which could one day mass-produce these advanced membranes at a competitive cost. The journey from a single square centimeter in a lab to thousands of square meters in a full-scale plant is underway, and the pace of innovation is accelerating. These nanomembranes are no longer science fiction. They are the tangible future of water purification. While refining pressure-based systems like reverse osmosis offers incremental gains, a truly sustainable future for desalination may require us to rethink the fundamental physics we employ. What if, instead of fighting against immense osmotic pressure with brute force, we could sidestep it entirely? This question is leading researchers down an exciting alternative pathway, one that works with thermal energy instead of mechanical pressure. Beyond the world of high-pressure pumps and energy recovery devices, nanotechnology is fueling a revolutionary model: membrane distillation. At its heart, membrane distillation, or MD, is a beautifully simple concept that mimics nature's own water cycle. It's a thermally driven process where the driving force isn't pressure but a temperature difference. Imagine a warm, saline feed water on one side of a special membrane and a cooler surface on the other. The temperature difference creates a vapor pressure gradient. Water molecules on the warm side evaporate, turning into pure water vapor. This vapor then travels across the membrane, leaving all the salts, minerals, and other non-volatile contaminants behind. On the other side, it comes into contact with the cooler surface and condenses back into high-purity liquid water. It's like a miniaturized, hyper-efficient version of evaporation and rainfall, all happening within a compact module. The magic lies in the membrane itself. Unlike the dense membranes used in reverse osmosis, MD membranes are microporous and hydrophobic, meaning they naturally repel liquid water. Think of it like a high-tech Gore-Tex jacket for water purification. The pores are large enough for water vapor to pass through freely, but the hydrophobic nature of the material creates a barrier that prevents the liquid salt water from leaking through. This is where nanotechnology makes a critical impact. Scientists are engineering these membranes at the molecular level, creating nano-textured surfaces with precisely controlled pore sizes and extreme hydrophobicity. These nano enhancements are crucial for maximizing vapor flux while preventing pore wetting, a key failure mode where liquid water breaches the membrane, compromising the entire process. The most profound advantage of this approach is its energy profile. Membrane distillation doesn't require high-pressure pumps, which are the primary energy consumers in RO systems. Instead, it runs on low-grade heat. This is a game changer. Low-grade refers to heat sources typically between 50 and 90 degrees Celsius, a temperature range where vast amounts of energy are often simply wasted and vented into the atmosphere. This opens up incredible synergies. An MD desalination plant could be co-located with a thermal power station, a data center, or a heavy industrial facility, running almost entirely on their waste heat. Alternatively, it can be powered directly by simple, cost-effective solar thermal collectors, which are far cheaper and more efficient at generating heat than photovoltaic panels are at generating electricity. This makes MD an exceptionally promising solution for decentralized, off-grid water production in remote, sun-rich communities. No massive electrical grid, no complex high-pressure equipment. Just the sun's warmth and smart membrane technology. Because it operates at low pressures and temperatures, the engineering and material requirements for the system are less demanding, potentially lowering capital costs compared to the robust, corrosion-resistant materials needed for high-pressure RO. Furthermore, since MD is a vapor-based process, its theoretical salt rejection is 100%. In practice, it consistently produces very high-quality water, often exceeding the purity of other methods, making it suitable for even the most demanding industrial applications. This gentle, low-pressure operation also makes the system more resilient to high-salinity brines and fouling-prone water sources that would quickly clog or damage an RO system, reducing pretreatment needs and maintenance downtime. It's a system built for resilience, efficiency, and synergy. The theoretical promise of nanotechnology is one thing. Its real-world impact is another entirely. Across the globe, the abstract concepts of nanopores and advanced membranes are hardening into steel, silicon, and polymer, tackling the water crisis head-on. These are not just laboratory experiments anymore. They are pilot plants, community-scale systems, and industrial testbeds, each one a crucial data point in the quest for sustainable water. From the hyper-arid landscapes of the Middle East to the tech hubs of California and the dense urban centers of Asia, a quiet revolution is underway. We're now moving from the what-if to the how-to, exploring the practical challenges and triumphs of deploying next-generation desalination technologies in diverse, demanding environments. Let's begin our journey in a region where water innovation is not just a goal, but a geopolitical necessity. Our first stop is Abu Dhabi, a global leader in large-scale desalination. While known for its massive reverse osmosis plants, the UAE is also a fertile ground for pioneering new solutions. Here, startups backed by entities like Masdar are deploying modular, containerized nanofiltration systems. These units are designed for flexibility, capable of serving remote industrial sites or supplementing municipal supplies. One pilot project, for instance, focuses on treating high-salinity seawater with a novel ceramic nanomembrane. Early data suggests these systems can operate with significantly lower pressures than conventional RO, leading to energy savings reported to be between 30 and 50%. The key is the membrane's unique structure, which offers high permeability without sacrificing salt rejection. This reduces the energy needed to push water through, directly lowering operational costs and the carbon footprint of each cubic meter of fresh water produced. In the same region, another technology is being tailored for the arid climate: solar-powered membrane distillation, or MD. Unlike pressure-driven systems, MD is a thermal process that uses a temperature difference to drive water vapor across a hydrophobic membrane. This makes it a perfect match for the desert, where solar energy is abundant. Pilot systems are demonstrating how low-grade heat, easily captured by solar thermal panels, can power the entire process. Some innovative projects are even co-locating MD units with factories or power plants, ingeniously using waste heat that would otherwise be vented into the atmosphere. This waste-to-water approach dramatically improves the overall energy efficiency of the industrial site. While MD systems currently have a larger physical footprint than RO for the same output, their ability to treat extremely high salinity brines and operate on low-grade, often free energy makes them a compelling option for specific off-grid or industrial applications. Crossing the globe to California, the nexus of drought and technological innovation, the focus shifts to precision and efficiency. Here, the challenge is not just producing more water, but doing so with the state's ambitious energy and environmental goals in mind. Research consortiums and venture-backed startups from Silicon Valley to San Diego are at the forefront of this effort. They are developing and testing advanced nanostructured membranes designed to combat biofouling, the Achilles heel of reverse osmosis. By embedding nanoparticles or applying specialized coatings, these membranes resist the buildup of biological slime, which allows plants to run longer between costly and chemical-intensive cleaning cycles. This extends membrane life, reduces maintenance downtime, and maintains lower operating pressures, all contributing to a lower levelized cost of water. California is also a key testing ground for the most anticipated breakthrough: graphene membranes. Collaborations between university labs like those at MIT and industrial partners are moving this technology from the beaker to the pilot skid. One such pilot plant, developed by a team spun out of the University of Manchester, is now testing scalable graphene oxide membranes. These membranes are not pure single-layer graphene, which remains difficult to manufacture at scale. Instead, they are formed by stacking layers of graphene oxide, creating a laminate with a highly controlled network of nanocapillaries. Water molecules can snake through this network with very little friction, while larger salt ions are blocked. The results from these industrial-scale tests are critical. They will validate not only the energy savings, with theoretical models predicting a potential for near-frictionless flow, but also the membrane's durability and resistance to chlorine and other operational stressors. Success here could unlock a step change in desalination efficiency, potentially making seawater desalination as energy efficient as treating fresh water is today. Our journey now takes us to Singapore, an island nation that has turned water management into a strategic art form. Singapore's Public Utilities Board has long been a global pioneer, particularly with its NEWater program, which recycles wastewater to ultra-clean standards. Here, researchers are aggressively exploring technologies like forward osmosis, or FO. Unlike RO, which uses hydraulic pressure, FO uses a natural osmotic gradient. A highly concentrated draw solution on one side of the membrane literally pulls fresh water out of a saline source. The challenge has always been the energy-intensive step of reconcentrating the draw solution. However, Singaporean researchers are piloting hybrid FO-RO systems to treat highly challenging industrial wastewater. The FO step acts as a robust pre-treatment, removing contaminants that would quickly foul an RO membrane, allowing the subsequent RO stage to operate more efficiently. This demonstrates a key theme in modern desalination. It's not about one technology winning, but about creating intelligent hybrid systems where each technology is used for what it does best. Finally, we travel to coastal communities in India, where the water challenge is often decentralized. Large, centralized plants are not always the answer for remote villages facing brackish groundwater contamination. Here, technologies like electrodialysis, or ED, are finding a niche. ED uses an electric field to pull salt ions out of the water through ion exchange membranes, rather than pushing water away from the salt. This makes it particularly energy efficient for treating brackish water with lower salinity levels. Teams are deploying small-scale, solar-powered ED systems that are robust, easy to maintain, and can be operated by local community members. These projects, often supported by NGOs and academic institutions, highlight a crucial aspect of water security. Technology must be appropriate for the scale and context of the problem. From massive industrial plants in the Gulf to village-scale systems in India, nanotechnology is providing a diverse toolkit, allowing us to tailor the solution to the specific need, ensuring that clean, safe water is within reach for everyone, everywhere. Nanotechnology is reimagining how we extract fresh water from the sea. It's not science fiction, it's the foundation for water security in a warming world. The question is not if, but how fast we can scale it. Which innovation will define the future of desalination? Graphene membranes or solar-powered distillation? Share your thoughts in the comments. Like and subscribe to Eco Innovatech for more on how technology is engineering a sustainable world.